Okay, we're back. This video, we're going to get some notes on nuclear power, fission and fusion. The other video was only going over the homework, okay, in case you wanted to split it up. Guess I'm too nice. Anyway, we ended up yesterday barely going over nuclear reactions, okay? Nuclear reactions are basically when we take mass and convert it into energy, and that energy is used to power our world, okay? There are two types that we're going to learn about today. One of them is fission, the other one's fusion. They are similar in that they both deal with nuclear processes, but they are different because one is splitting and the other one is joining, okay? So, nuclear fission is the first one. That's splitting. That's splitting of nuclei. Gives off energy and particles. And what happens here is the particles, and specifically neutrons given off, can be used by other nuclei and cause a chain reaction. It can cause a chain reaction. Now, chain reactions can be one of two sorts, and we'll look at that here in a second. If they are controlled, then we can use them. If they are not controlled, we can use them for the ultimate destruction with something like a nuclear bomb. Okay? So, controlled can be used by nuclear reactors, like the one in 9 Mile Point up in Oswego, and in uncontrolled nuclear bombs. Causes a chain reaction, and that chain reaction just releases all kinds of energy, like we did in 1945 in Hiroshima and Nagasaki. Okay, so what happens here? Here's a typical fuel for nuclear reactors, uranium-235. So when it gets hit by a neutron going fast enough, it will split it. And when it splits it, it releases energy. Okay? It releases energy. When this happens, you get things coming off of this. They're called fission products. And we'll do some examples. One of the fission products is going to be a lighter element. So in this case, we start with a heavy element and we end up with lighter elements and some particles like neutrons. So what happens is once one of them splits, these neutrons have enough energy to go and hit another uranium-235 nucleus and cause it to split, which causes another series of neutrons to be released, and it continues from there. Okay, that's called the chain reaction part of it. All right? So fission is what is used by nuclear power plants today. And what's used most is uranium-235 or plutonium. And these are what we call fissionable. In other words, they can be broken apart to yield energy. They are fissionable. All right? Now, we'll talk about risks more specifically down there, but right now, risks involved in using radioactive isotopes, you could get exposed to that. If you work up there in Oswego someday, to the nuclear power plant, they're going to give you a tag, and the tag will show you how much radiation you've been exposed to. If you're exposed to too much, above a certain level that the government has decided is safe, then you have to go home. Okay? So biological exposure is going to be an issue. There's also the issue of storage. Storage is important because half-lives can be very long, and we don't want radioactive materials just dumped somewhere. Storage and disposal. And of course, there are nuclear accidents that have occurred. Probably the three most famous right now are 3 Mile Island, that was in Pennsylvania in 1979. In the Ukraine, there was Chernobyl. I think I spelled that right. It might be BYL, sorry. Chernobyl. This was in 1986. That was a huge one. And more recently, in Japan, in the Fukushima, after the tidal wave, the tsunami that came through about 2009 or 2010. Okay? So, how do I recognize an artificial transmutation? Well, if it's a natural transmutation, you're only going to have one reactant. Then you'll have products. If you have an artificial one, you'll have two reactants. That means I'm hitting this with this. Okay? So if there are two products and or reactants, and then you end up with products, it's going to be an example of an artificial transmutation. In this case, it is a fission, because I start with something big and I end up with smaller things. Now, what was true with the other nuclear reactions, the natural ones, these numbers here still have to add up to these numbers. Okay, so 92 has to be my total on the bottom. 35, that's 35 is 80, that's 92, and then 0. So 92 works. I still have to balance this, 236. So 4 of these, so 4 is 150, 236. Okay? All right. So we'll do some practice balancing those as well. So that is fission. That's what happens in nuclear reactors. That's what happens when nuclear bombs are exploded. The other type is fusion. Fusion is the combining of light nuclei. So fission, taking big nuclei and splitting them. Fusion, taking smaller nuclei and having them fuse together. These reactions occur in the sun and any other star. Okay? And when this happens, huge amounts of energy is released. And on Earth, the fuel for this is plentiful. There's lots of it. Deuterium, which is water, that's heavy water. Deuterium is hydrogen, except it has one neutron and one proton. Okay? Regular hydrogen has one proton and 0 neutrons. So it's found in all ocean water. There's plenty of it. A big advantage for nuclear fusion is it does not result in radioactive waste products. So there are waste products at first that are radioactive, but almost immediately they will become non-radioactive. Okay? Here's the challenge, though. We haven't gotten it to work. The idea is there, and they have come up with spent huge amounts of money to try to get this to work, because once it does work, we won't need fossil fuels, wind, nothing. We won't need anything except this, because it will generate so much energy. So I have not been able to contain extremely high temperatures and pressures. Both of these things have to be there in order for these atoms to come together. Deuterium is H2-1, and tritium is another one that's H3-1. This has 2 neutrons. Okay? And what happens? You end up with helium. So hydrogen becoming helium releases huge amounts of energy, and then you also get a neutron coming off of that. All right? So they also produce more energy. More energy, that's a question that you're going to get. Produces more energy than nuclear fission. And here is the example that's shown graphically there. Deuterium plus tritium yields helium and a neutron. Okay? So those are the differences between fission and fusion. Fission, splitting apart to release energy. Fusion, bringing atoms together to make a bigger, heavier atom, and that releases even more energy. All right, let's take a look at your homework, which is going to be the odds on artificial transmutation, which is here. Okay, it looks like this sheet here. Nuclear equations for artificial transmutations. I want you to do the odds, and really it's not that much different. Let's do number 2 together. 63 plus 1 is 64, yes? So if I bombard a copper atom with a neutron, it's still going to have 4. I still have to have 4. 60 plus 4, 63 plus 1. 29 plus 0 is 29, so you know that the bottom here is going to be 2, and hopefully by now you recognize that 4-2 is a helium, and that's an alpha particle. All right, so do the odds, including number 9. It's still just adding it up, and then you have to look in your reference table. All right, today's Thursday, so tomorrow we'll pretty much finish, and then Monday we will review. Take care.